Before the cloud, a new application required a completely new physical server. This created a sprawling, chaotic landscape of hardware silos, where hardware was permanently dedicated to a single specific task. If that server only used 10% of its processing power, the remaining 90%. The hypervisor is the software layer that makes this possible. It sits between the hardware and the virtual machines, intercepting requests for CPU power or memory and deciding which piece of the physical hardware to allocate. In large-scale data centers, we use Type 1 or bare metal hypervisors. These are installed directly on the hardware. By removing the middleman operating system, they provide the high-speed performance required by providers like Google and AWS. Developers often use Type 2 hypervisors directly on their own personal laptops to securely test their new application code. These run as an application inside an existing operating system, which is convenient for local work, but less efficient for heavy data center workloads. Virtualization enables workload portability. It allows a running environment to move from one physical machine to another without the software ever knowing it shifted. Even with virtualization, a sudden spike in traffic, like a viral event, can overwhelm a system. Handling that load requires a specific scaling strategy. One option is vertical scaling, replacing your server with a more powerful one, but eventually you hit a hardware ceiling. Instead, horizontal scaling adds hundreds of smaller machines to share the workload. Because it is distributed, if one breaks down, the others keep moving seamlessly. Horizontal scaling allows for growth far beyond the limits of a single machine. However, it only works if the underlying software is designed to function across a decentralized network. Traditional monolithic software is often too rigid for the cloud. To operate effectively, engineers use a service-oriented architecture, or SOA, which follows three specific rules. First, loose coupling connects independent modules via thin APIs, so updates don't break the system. Second, abstraction hides complex backend processing behind a simple user interface. Third, reusability allows a single service to be shared by shipping, marketing, and developers simultaneously. This transforms software into a flexible ecosystem of specialized tools, matching the resilience of the decentralized hardware beneath it. Once the infrastructure is scalable and service-oriented, it allows for a higher level of automation at the enterprise level. This is Business Process as a Service, or BPaaS. While standard software gives you a tool, BPaaS gives you a result. It automates an entire end-to-end outcome, such as payroll processing or global logistics. BPaaS providers bundle modern technology like AI and machine learning with economies of scale. This allows companies to replace rigid in-house administrative functions with agile, subscription-based services. By utilizing this layer, a company can focus on its core competency while the cloud handles the operational context. Each layer of the stack solves a specific problem. Virtualization conquered hardware constraints. Horizontal scaling bypassed traffic limits, and SOA removed software fragility. This architectural progression has led to the modern cloud environment, a system of automated services that can adapt to demand in real time. By decoupling the technology at every layer, engineers have created an environment that allows infrastructure to adapt as a business evolves.